Azimishni Vedalwa.
İşte stüdyoda. Allah. Yes, go back. Mobile. New. Paper. It's okay. Yes. Now it's 50. Okay. Okay, now let's start with the new lecture. In the previous week, we have talked about the co-channel interference and the relationship of the S over I, which was square root of a 3n raised to n small divided by I naught. And we have said that I naught represents the number of cells which will interfere a given mobile at a specific cell. Today, we are going to continue with this concept, I mean the co-channel interference. We have an example. First of all, I'm going to solve this example, a numerical example.
الدكتور سكرين شير هكذا عملنا بيت
شو؟
سكرين شير
يعني كده شبكة. الو الو.
دكتور تبي دي في فاكرينك اودي محاضرة
يا زلمه بي دي اف طبعا بي دي اف بي دي اف بي دي اف.
انت اكزامبل شرح كم لا موجود ده
انا دي دخلك بس خو بقرا بي دي اف كادي بيج متى chapter 3 بس بري خوبدن. Okay, the textbook, your textbook. Okay, this textbook, look at the textbook, wireless communications principles and practice, second edition, Theodore S. Rappaport. Chapter, we have covered the chapter 1, and by now we are going to talk about, say, we have dealt with about 60% of this chapter again. Okay, so just I want to be aware of that we have covered about more than 50% of this chapter. Okay, all of these are taken. Now, that was about the co-channel interference. Okay. Here we have an example. Look at this example. Yes, it's very okay. Now, look at this example. If a signal to interference ratio of 15 dB is required for satisfactory forward channel performance of a cellular system, what's the frequency reuse factor and the cluster size that should be used for maximum capacity? If the path loss exponent n equal to 4, then n equal to 3. Assume that there are 6 co-channel cells in the first tier, and all of them are at the same distance from the mobile. Use suitable approximation. Now, first of all, we have to discuss the important points in this example. At the beginning, in this example, we have two branches. Branch number 1, or A, talks about path loss exponent n equal to 4, and in B, n equal to 3. Really, we are going to study in this example, of course, we are going to study the effect of path loss exponent on what? On the system performance. And we have fixed the signal to interference noise ratio, look, which is 15 dB. So less than 15 dB will not be acceptable. Okay, at least we have to what? We have to have 15 dB, not less than 15 dB. So what's the missing parameter in this example? Of course, n capital. Okay, n capital, we are going to determine n capital for both cases. I mean, when n equal to 4 and n equal to 3. Again, we have to keep in our mind when we are going to determine the, say, the frequency reuse or the cluster size that should be used for what? For maximum capacity. Of course, what do you mean by maximum capacity? As you know, a smaller cluster size will what? Will maximize the what? The capacity of the cellular communication system. So we have to have a cluster size which will lead to S over I greater than 15 dB, and on the same time we have to satisfy the requirement for maximum capacity of the cellular communication system. Of course, as you know, first of all, we have to what? We have to convert the 15 dB S over I, 15 dB we have. First of all, it must be converted into ratio. Then we are going to solve the problem. Now, let's go to whiteboard, of course, to be able to deal with this problem. Full screen. Okay, now as I think you see the whiteboard. ها درسته جماعة؟
بلي دكتور.
Okay, now how we are going to determine the dB for a given, for example, signal to noise ratio or anything else, or signal to interference ratio? S over I generally will be 10 log, of course, base 10. Okay, 10 log base 10 S over I. So when you are going to determine S over I in ratio, at that time S over I in ratio will be 10 rise to power 1.5 in this case. Okay, or if you need more explanation, okay, I can we can substitute now 15 here. 15 dB equals to what? 10 log, okay, S over I. So first of all, 10 taken to the left hand side, it will be 1.5. Okay, I mean divide the both sides by 10. We have 10 log S over I. This means that S over I will be 10 raised to power 1.5. Okay, now we can determine the 10 raised to 1.5. It will be 31.6227. Okay, now first step, what we have done in the first step, we have determined the ratio of the S over I mean converting from dB into ratio. Well, now again in the problem, the requirement are what? Two things really: the reuse distance, okay, and what? And the cluster size. Keep in your mind that reuse distance is what? D over R equals to what? Square root of 3n. Of course, this will be the reuse distance. Okay, and what? And n is missing. So we have two things are missing: D over R, which is the reuse distance, and n capital, which is the cluster size. Now, let's go to the solution. Now, S over I, as you know, in the previous week, we have talked about this relation. S over I equals to what? Equals to square root of 3n raised to n small divided by I naught. And we said that in the previous week. How many interfering cells we have? أري ما چند هي؟ I naught چنده مفروض. In the case of omnidirectional antenna, I naught must be 6. Okay, so I naught already is known. Okay, I naught equals to 6. N small is given in different values. For n small is given n equal to 4, then n equal to 3. Now let us go to the branch A. In branch A, n small equal to 4. Now substitute in the previous equation. So we have 31.6227 equals to square root of 3n. It means square root means what? Rise to power 1 over 2. Then it will be rise to power 4 and divided by what? Divided by 6. Is it clear or not? No response. Okay. Now, what we are going to do now? Now we are going to multiply 31.622, okay, by 6, okay. So it will be 189.73 equals to, look, rise to power 1 over 2 multiplied by 4, so it will be 3n all squared, okay, 3n all squared. Now we can further simplify the equation. Now 189.73 equals to 3n, and this will be 13.77. 4 equals to 3n. This means that n equal to 4.59. Okay, now according to the numerical calculation, n capital equals to 4.59. okay, n equal to 4.59. Now what will be the actual value for n capital? Do you know or not? Is there cluster size in terms of fractions? أري جماعة. Is there cluster size in terms of... ها؟
الدكتورة حفظ وظيفتها هنا.
Okay. According to the equation, okay, we have n equal to what? I squared plus ij plus j squared. Okay. So we have a set of cluster sizes. For example, 3, 4, 7, 9, 12. Okay. These are some of the cluster sizes, of course, according to what? According to the equation of I squared plus I by j plus j squared. Now you have the following cluster sizes. Now, are you going to approximate n capital to 4 or to 7? You know, we don't have fractions. يعني منينا مثلا cluster size char ونيف char point half منينا لازم رقمك integer. Okay, n capital must be an integer number. Now, what we are going to do, are we going to approximate the 4.59 to 4 or to 7? وطبعا why? I'm waiting for your answers. كاكاروش، كعمر، آريان، آيسن. ها؟
دكتور بيتحافظ بتن ضغط سرچنا بتن
چاو برا؟
بتنم رقم بتر ورگیرین دا گلک اودیل سر بیسا چنا بتن
يعني رقم شاند، يعني قيمتك يبدا
حفت.
من قلت يعني يا
حفت.
شار يا حفت.
حفت
بوشي حفت.
چینکو هکا چار بت دک تحمل نکن
يعني ان شاء الله تناقهم، يعني از تناقهم بما توضحك ايش توضحك اگر شار بدي بتشند
يعني بتنم رقم مصدر ورگیرین دا شد تحمل لودی بکت
كيش لوده؟
السيجنال
لا، او طبعا او حفت درسته يعني حفت، بس يعني واي نقلك واضحه في راستي بجمته. another one help me another one. اري جماعات، يلا ما شاء الله يا معود تشن كسن بالله كان صح به ما شاء الله. حفتي هش طالبه ميتين تقريبا، حشتي طالبه. يلا شار يعني حفت وبوشي.
سيداك تشور بي كوباستي تيرانا قد بكينا حفت
كاباسيتي وشار كمان شار يعني بو
لا
كاباسيتي.
ديك حفت تشور بتيرانا قد مثلا في ماستر والجرين
يعني بوشي
يبقى كوباستي نوتش بكينا تشار
نا خير بر كاباسيتي بو كاباسيتي كيف شار كريستال سايز شار تشتري بو كاباسيتي طبعا كان كلاستر سايز
دكتور نادي في سيجنال تو انترفيرنس ريشيو اتشنكم بازدا دي بي مينيمم بو
اوف عافيه اريان ابا اريان انا
بله دكتور
عفر ماريان نوكا شرطي اصلي تشتا شرطي اصلي شيا من قلتها ما هي 15 دي بي كم ترش 15 دي بي تشينابت. Okay, look, we have what? We have determined n capital 4.59. Okay, 4.59. So 4.59 will lead to 15 dB exactly. Okay, now if you are going to approximate the n capital to 4, what will happen? Be sure, okay, that the S over I will be less than 15 dB, and this is acceptable. Okay, so what we are going to do, we are obligated really to what? To select the cluster size equal to what? Equal to 7. Well, so n capital will be what? Will be 7 cells. Now, of course, at home, you can what? You can try by your hand. Okay, try to check n capital equal to 4 and find out S over I in dB. Of course, it will be less than 15, and then resolve the problem and use n capital equal to 7. You will see it will be greater than 15 dB, which is the acceptable value. So due to the numerical value obtained from the equation, we have 4.59, and this one will not be acceptable. The approximation will be to the what? To the higher cluster size for what? To satisfy the requirement of the problem, which is what? Which is the 15 dB at least. Well, remaining is what? Remaining is the D over R, which is the what? Which is the reuse distance or ratio. It will be square root of 3n, and this will be 3 multiplied by 7 and square root of 21. Okay, so we are going to determine the square root of 21, which is 4.582. Okay, D over R. Of course, this will be unitless. Why? D represents the distance between what? Between the centers of two cells which have the same channel set. Okay, this is D. And R will be what? Will be the cell radius. Okay, cell radius. And this will be co-channel distance. Okay, co-channel distance. Well, so D over R, co-channel distance will be in meter, okay, and R will be again in meter. So D over R will be unitless. This is about what? About the first branch, I mean A. In branch B, we are talking about what? Another path loss exponent, which is what? Which is 3. Now we have cluster size again is missing. Now n is missing, and we are going to use another path loss exponent. Look, again, we are going to follow the same equation, which is what? S over I equals to square root of 3n raised to n small divided by I naught. Substitute directly 31.622 equals to what? Equals to square root of 3n raised to power 3 divided by 6. Okay. Now we can simplify the equation. It will be 31.622 multiplied by 6, 189.732 equals to, look please, 3n raised to power 1 over 2 to power 3. In other words, it will be 189.732 equals to 3n raised to power 3 over 2. Okay, now how we are going to get rid of from the 3 over 2? We are going to raise the both sides of the equation to 2 over 3. Okay, so it will be 189.732 raised to 2 over 3 equals to what? Equals to 3n. Now I'm going to calculate this one, this factor 189.732. Okay, rise to 2 divided by 3. Okay, now it will be, the answer will be 33.018 equals to 3n. As you can see, n capital will be about 11.006. Okay, now this will be the n capital for the second branch. Look please, now again we don't have cluster size of 11, we have 3, 4, 7, 9, 12. Okay, the nearest cluster size to this value will be n equal to 12. Okay, so n capital will be 12 cells, and the D over R reuse ratio will be square root of 3n, and it will be square root of 3 by 12, and it is 36. يعني بتشندا 36 square root of 36 chanda array square root of 36 ها okay, so it will be 6. Now my question is, what you can conclude from this example? What we can conclude?
وقتی اکسپوننتی کم دکین
شو بدنا نجي خب شيء بلندك
وقتی این اکسپوننت کم دکین
إيه؟
او reduce distance هكذا زيادة دبيتن
بالضبط. يعني in other words, path loss exponent will directly affect on what? On the S over I. Okay. If path loss exponent is increased, then S over I again will be increased. Okay. Again, increasing n small, we can consider a smaller cluster size. Considering smaller n small, we can what lead to larger cluster sizes. In other words, the n small will directly affect on what? On the capacity of the cellular communication system. So larger values for the n small will lead to what? Higher capacity, and the smaller values of n small will lead to reducing the capacity of the cellular communication system. This is about an example of this book, really. It's a very important example, really. Now we are going to go back to the lecture. Okay. Now that was
بس بسعر زحمة نبي
هابري كرمك
بس اي نوت دائما شاشة يعني حسب سعر الجوال
حطانك اي نوت شاشة. اوكي. ان شاء الله يعني حفتيابات او يعني ايش ده ما موضوعك هي لسر enhancing of the capacity of the cellular communication system. At that time we are going to consider sectoring. حالتها sectoring I not دي بدل بت. اوكي بس حطانه كان I not ثابتة شاشة. اوكي. In other words, when you are using omnidirectional antenna, I naught will be 6. That's it. Well, now this is about this example. Then we have the following topics: cell planning, and we have adjacent channel interference. Okay. Now I'm going to talk about the adjacent channel interference. Of course, you have a lecture and slides, but at the beginning, I'm going to show you some important things in the book. As you know, we said that we have two kinds of interference, co-channel interference, and we have dealt with the co-channel interference in the previous week. In this week, inshallah, we are going to talk about the adjacent channel interference. Co-channel interference will affect on the control channels. Adjacent channel interference will affect on the traffic channels or the voice channels. Now, how we are going to minimize the effect of the co-channel interference? Of course, by what? By considering larger cluster sizes. In other words, providing sufficient physical distance between co-channel cells, okay, or increasing the physical distance between co-channel cells will lead to what? Will lead to minimizing the co-channel interference. Now, in the case of the adjacent channel interference, we are talking about what? We are talking about channels which are what? Which are lie inside the same cell. So in this way, how we are going to overcome the problem of adjacent channel interference? By what? By providing sufficient guard band between adjacent channels. Of course, whenever you are going to provide sufficient guard band between the adjacent channels in the same cell, at that time you will lose a lot of what? A lot of channels, and this will lead to what? Reducing the capacity of the cellular communication system. So we have to find techniques, ways by which we are going to what? We are going to arrange the channels or assign channels, allocate channels for what? For given cells. Let me show you the lecture which talks about the adjacent channel interference, and then we will study or learn how to distribute or make cell plan for the system. Interference from first tier and second tier co-channel cells. Look, please, in the previous week, we have talked about what? We said that, say, the red cell, we have a mobile unit at red cell, and this mobile will collect interference from the what? From the co-channel cells. Look, if you have the following clusters in the system, of course, we are talking about a cluster size of 7, so every cell has 6 neighbors. Well, look at the red cell, and we have here green cells. These green cells, if you are going to count these green cells, they are what? They are 6. Okay, so in the first tier, we have 6 co-channel interfering cells. Really, if you are going to move to the what? To the second tier, we have what? We have 12 co-channel interfering cells. Okay, now in this course, really, we are going only to talk about what? About the cells which are what? Which are in the first tier, not all of the cells. Why? The ratio between really the second tier and first tier will be explained here. Look, we see that there are 6 first tier co-channel cells that are all equal distance from the central red channel. Assume that the distance between any centers of the first tier co-channel cells and the central cell is D. As you know, we said that the distance between 2 co-channel cells is what? Is D. We have defined previously. The second tier co-channel cells are not all at equal distance from the central red cell. There are 6 that are located at 2D from the central of the cell, and 6 others are at distance of 1.73D. Of course, this calculation based on the what? On the hexagon shape. Now, this will give the interference ratio of the second tier to the first tier co-channel cells according to this equation. Okay, 6 multiplied by 1 over 2 to power 2d to power n small plus 6, which has distance of 1.73d to rise to power n small. And of course, in the first tier, you know, when we talk about the same distance, we have 6 multiplied by 1 over d to power n small. Now, taking different values for n, look, n equal to 2, n equal to 2.5, 3, 3.5, and 4. Basically, typical values for n small will be between 3 and 4. Look, when n equal to 2, the ratio between second to first tier is 0.5. 2.5 is 0.4. Now, which is, if in the case of a 3, it will be 0.3, 1.8. 3.5, it will be 0.235, and in the case of the n equal to 4, it will be 0.17413. Really, as you can see, this is the ratio between what? Between the second tier interference to the first tier interference. So practical values for n will be 3 to 4. The ratio of the interference of the second to first tier co-channel interference is less than 1 over 3. Therefore, we will ignore it in this course. I mean, the second tier interference will be neglected. Well, now, some notes regarding to the co-channel interference. Look, the radius of the cell has no effect on the what? On the SIR, because the radius of the cell increase, the distance of the cell increases. For example, the location of the corners of the cell moves away. The same ratio, the co-channel cells move away. Path loss exponent really has a profound effect. As you can see in the previous example, we have studied the effect of n small. Okay, the higher value of n, the higher SIR, and vice versa. So the fact that the airband region, the value of n is greater than the free space n of 2 is unacceptably beneficial. Okay, so we will make use of this thing, I mean, when n is large. To get an acceptable value of S over I around, okay, 18 dB or so, we need a cluster size at least of 7 and path loss exponent around 4. Okay, really we have two standards. Some of the systems accepts 15 dB signal to interference noise ratio, and in other systems we have 18 dB at least. Basically we have European and US standards. In advanced mobile phone system, the acceptable signal to noise ratio is 18 dB, and in the GSM or European standards, we have 15 dB. The distance between one of the corners of the central cell and the interfering co-channel towers become simpler to compute when I equal to 0, because of the symmetry where each of two cells will have the same distance. Of course, I equal to 0 means what? Means we are working with the linear cell distribution. I mean, in the I and J in the N capital equation. Now, that was about the second tier and first tier. As I think now you can imagine what do you mean by first tier and second tier signal to interference noise ratio. Now let us talk about the second kind of the interference, which is the adjacent channel interference. Unfortunately, co-channel interference is not only the type of interference that mobile system suffers from. Another type is called adjacent channel interference. Of course, you have to be able to make differences between what? Between adjacent channel interference and the co-channel interference. At least you have to, for example, list 3 differences between these two kinds of interference. Now, this type of interference occurs not because of mobile phone or cellular towers in different co-channel cells transmitting signal at the same frequency, but it occurs because of the mobile phones in the same cell transmitting signals at different but close adjacent frequencies, that the cellular tower has difficulty in filtering out the different channels from each other. Now, we said that again, the co-channel interference occurs where? In the forward channel received by the mobile unit. Although co-channel interference occurs in the what? Reverse channel received by the tower, it is harder to study the co-channel interference in the reverse channel because the difficulty of locating the mobile phones in the different co-channel cells. Now, please look at these two lines. Previously, when we studied the interference effect on the mobile unit, we have what? We have fixed distance. Okay. Now, if you are going to study the co-channel interference on the reverse, for a reverse channel, I mean to the towers, it will be very difficult. Why? The locations of mobiles are not determined. Okay, so the reverse effect of the co-channel on the reverse channel will be very difficult. Now, adjacent channel interference is only a reverse channel problem. To illustrate why, look please, we have different scenarios. In these different scenarios, we are going to illustrate the effect of the adjacent channel interference. To illustrate why it's occur, consider first real signal filters. Real filters never have zero width transition band. In the previous year, as I think, if you remember, we have studied the filter design, and we said that any filter has 3 regions: band pass region, stop band region, and in between we have transition region. Okay, now the width of the region between the pass band and the stop band is never equal to what? Never equal to 0, and their stop band levels are never 0. The filter attenuates the undesired signal, but not completely. Therefore, extracting a channel from a set of channels that are adjacent is never a perfect process, because part of undesired adjacent channel also passes where? Through the filter in addition to the desired signal. I mean, there is what? A leak into the band of the what? Band of the desired channel. Also, the closer the channels are to each other, the smaller transition band is, the more difficult in the what? In the construct the filter. Really, now we have two scenarios in a cell. Now I'm going to talk about the first scenario, then we'll take a rest and talk about the second scenario. Look, this is the tower, okay? Now we are talking about the signals received by the tower, okay? Signals which are received by the tower. Now, consider the case where there are 10 mobile phones that are communicating with a particular tower using the channels, consecutive channels. Well, look, now in this scenario, look, all mobiles, okay, are at the same distance from the tower. Of course, we don't have such a case, but just for what? Just for analysis and to understand what's going on. Now, because all mobile phones are located at equal distance from the tower, the power received at the tower due to each mobile is almost the same. Look, please, here in this scenario, we are assuming that we are going to measure the power received from all mobiles where? At the tower, okay? So we are locating the power meter where? At the tower. And we are receiving continuously, okay, the received power from all mobiles, the 10 mobiles. Now, the spectrum, okay, the spectrum or magnitude spectrum of the channels, okay, at the tower end will be as follows. Look, y-axis represents the power received and x-axis will be the frequency, I mean channels. Look, mobile number 1, 2, 3, 4, 5, up to 10. We are measuring the same amount of power for what? For all channels or for all mobiles. Now, assume that we are going to extract the mobile 5, okay? The mobile 5, and we are going to what? To attenuate all others. Now, to extract any of the channels, for example, mobile 5, and reject all other channels by attenuating by around 20 dB. For example, a simple filter can be used in the following form. Look, here we have a filter. As you know, in the distance between the passband region and the stopband region is 20 dB. So after passing this spectrum, the whole spectrum, okay, to the bandpass filter, the result will be as follows. Look, mobile 5 is amplified by 20 dB, while the other channels are what? Are attenuated by 20 dB. So easily we can what? We can extract mobile number 5. Really, this is what? This will be the first scenario. Second scenario, we have another scenario. Now let us take a rest of 10 minutes and we will go back to continue with the second scenario. If you have any question by now, you can ask your questions, please, about the adjacent channel interference and the first scenario. And I'm ready. I'm going to hear from you if you have any questions. كرمكم جماعة. Jamaat, any question? Do you have any questions? Do you have any questions, please? Okay, now take a rest for 10 minutes and we'll go back to the second hour. Okay.